And now here at Breaking Software Track, we will have Paul Sabanal and Mark Yason talking about playing the Radar versus Sandbox. Let's give them a warm reception.
Good afternoon, I'm Paul Sabanal and this is Mark Yason. We're both from IBM X-Force Advanced Research, and today we're going to talk about the Adobe Reader X Sandbox. Late last year, Adobe released Reader X to mitigate, in an effort to mitigate exploitation attempts against Adobe Reader. And so far, we can say that it is a success, as proven by the lack of exploits that fully compromises an attack system. And in fact, in the last few months, there were a couple of 0 days that could affect Reader X, but they weren't able to fully compromise the system because of the lack of sandbox escape and or bypass techniques. And in fact, as of this time, there are still no publicly known sandbox escape or bypass method. However, having said that, we wondered if there's still anything malicious that can be done in spite of the restrictions imposed by the sandbox. Since most of the attacks nowadays are financially driven, we wondered if from an attacker's perspective, we wondered if there's still something that can be done to bring profit. And from a user's perspective, what should we still be wary of, or what should still be watch out for? So these are the core questions that we asked ourselves when we first started this research. And we also were curious about any potential sandbox, bypass, or escape technique. And we were also hoping if we can find any. So the first half of this talk is about the sandbox internals. Since we enabled to answer those questions, we had to understand the implementation details of the sandbox. And that's the focus of the first half of this talk. We also needed to understand the potential weaknesses and limitations of the sandbox, and that would be the focus of the second half of this talk. But before we go into detail about the sandbox internals, we would like to talk about something that made this research a lot more easier than it should be. It's the relationship between Google Chrome's sandbox and the Reader X sandbox. When we started this research, we were aware that Reader X Sandbox is based on Chrome's, but we didn't know to what extent. It's just the design or the technology, or was there code shared between them? So when we were looking at the Reader X binary, we noticed some debug strings that looks like it's pointing to Chrome source code. So what we did is we compiled a release build of Chrome with debugging symbols on, and using the patch diff 2 plugin in IDA Pro, we binary diff it against the reader binary, which is acro rd32.exe. We also used some in-house scripts to see if to improve the results, and the results were quite interesting. And we indeed verify that there's code reuse between Chrome and Reader X. But also, we needed to verify the results. We can't just assume that it's a perfect match. And we also needed to see if there's some subtle differences between the match functions. So there was also a lot of manual analysis on our part. So in the Chrome source code, the most sandbox functionality resides under the sandbox namespace. And out of 291 functions that can be found in the Chrome binary that is under the sandbox namespace, 276 matched with the functions in the Reader X binary. There was also a lot of utility functions that match as well, such as portable executable parsing functions and some debugging functions. Then we ported the match function names from the Chrome IDB to our reader IDB. Another thing that helped us in our reversing process is the use of a tool we developed which does dynamic object reconstruction. It is based on the PIN dynamic instrumentation tool, and what it does is reconstructs C++ objects dynamically. It allowed us to see the target functions of indirect calls and which objects calls them and which constructor for the object which constructor for the object that calls them, so we could identify the class. We applied this to both the Chrome binary and the reader binary before we did the binary diffing, and we applied the results to the IDBs. We added cross-references from the indirect call sites to the target functions, and that helped improve the binary diffing results since the algorithms rely on call graphs. And after we did all this, we had a nice disassembly to play around with, and now we can start to look into the more details of the Sandbox internals. But before that, I'm going to talk about the Sandbox architecture for a bit. There are two main components in the Sandbox, the broker process and the Sandbox process. The broker process is responsible for setting the policies, the restrictions, and for spawning the Sandbox process. It also hosts the IPC service that is used to communicate between the Sandbox process and the broker process. The Sandbox process, on the other hand, it contains all the code that should be sandboxed, and it is responsible for parsing and rendering the PDF files. It also hosts the IPC client used to communicate with the broker process. We will go into more details about each component in the rest of the talk.
All right, before moving on, we will have a quick overview of the restrictions set on the ReaderX Sandbox process. The ReaderX Sandbox uses three windows mechanism to restrict the privilege of the Sandbox process. There are restricted tokens, integrity levels, and job objects. Notably, the ReaderX Sandbox does not use a separate desktop for the Sandbox process. Instead, it mitigates attacks such as shadow attacks and DL injection via the other listed Windows mechanism. Notably via integrity levels, which is used by the User Interface Privilege Isolation feature in Windows Vista, or UIPI. UIPI prevents low integrity process from sending messages to windows of higher integrity processes. UIPI also prevents DL injection to higher integrity processes. The Sandbox process uses a stripped-down token. Note, however, the Sandbox process token is not the most restricted compared to the one used by Chrome, since it still has access to some resources, such as those accessible to the everyone in users group. Also, the integrity level of the Sandbox process is set to low, which prevents it from writing to most resources, since most resources have a medium or high integrity level. Finally, the Sandbox process is also associated to a job object, which restricts additional capabilities, such as spawning new processes, changing the display settings, and so on. Notably, access to the clipboard and the global atom table is not restricted.
Okay, so now let's talk about what happens when a PDF file is opened. First, the broker process will be spawned. Then the broker process will set up Sandbox restrictions for the Sandbox process. First, it sets the job level to job restricted, but with the following restrictions unset. A job object UI limit with clipboard, which allows the Sandbox process to read from the clipboard. Job object UI limit write clipboard, which allows the Sandbox process to write to the clipboard. And job object UI limit global atoms, which gives the Sandbox full access to global atoms. The job level is actually one of the things that differs with Chrome. Chrome doesn't unset anything, and Chrome's job level is set to job lockdown, which has basically the same restrictions with job restricted, except that it kills the sandbox process when an unhandled exception occurs. Next, it sets the token level. The token level of the token used by the sandbox process is called the lockdown token, and is set to user limited. However, during process bootstrapping, the OS loader needs to access some resources that may not be accessible if it uses the lockdown token, which is a lesser privilege token. So just during the process bootstrapping, there's an additional token which is used, which is called the initial token. It is set to user restricted same access for Windows Vista or later, or user unprotected for Windows version prior to Vista. The initial token will be discarded later on after the critical initialization is done. Next, it sets the integrity level to integrity level low. Then the broker process adds the DLL eviction policy, which is a list of DLLs known or suspected to cause the sandbox process to crash. These DLLs will be unloaded by the sandbox when detected. Below is the list of is a short portion of the DLLs that will be evicted. In the current implementation, there's about 46 such DLLs, and you can see the full list in our white paper. After this, the broker process sets up the generic policies. It sets up the admin configurable policies, which it reads from the protected mode whitelist.txt file. Then it sets up the hard-coded policies. We will go into more detail about the policies later on. Then the broker process spawns the sandbox process in a suspended state. In this state, it sets up and initializes the interceptions or hooks in the suspended sandbox process. We will talk into more detail about the interceptions later. After this, the broker will resume the suspended sandbox process. And as we mentioned earlier, during the process startup of the sandbox process, two tokens are active, the initial token and the lockdown token. And somewhere when the sandbox process resumes execution, somewhere along the way, there will be a call to the lower token function, which is responsible for discarding the initial token, and that leaves us just the lockdown token active. And by the time the full restriction of the sandbox is in effect.
Okay, after discussing the sandbox restrictions and startup sequence, we will now take a look at the major components of the ReaderX sandbox. The first component is the interception manager. What does it do? It is basically the mechanism that forwards API calls to the broker. It does this via API hooking. Generally, failed API calls resulting from the sandbox restrictions are forwarded. An example would be a sandbox process needing to open a PDF file from the user's desktop. Since the sandbox process token have no access to files in the user's desktop, the API call would need to be forwarded to the broker, which in turn evaluate the access if the access is allowed or not. And if it is, it will open the file for the sandbox process and return the handle duplicate back to the sandbox process for its use. There are different types of interceptions. For NTDLL APIs, the interceptions looks like the one on the screen. EDX is set to the address of the thunk code, which sets up the stack and performs the actual transfer to the interception handler. The interception handler, on the other hand, is the main code that forwards the API call to the broker. There's also another interception type in which interceptions are performed in the export address table. There's also another type which involves patching the entry point of APIs with a jump instruction. Finally, there's a special interception type for unloading DLLs, which are suspected or known to crash the sandbox process. Maybe because these DLLs are not suited to run in a restricted environment. Instead of patching APIs in these DLLs, the DLLs are unmapped from the sandbox process. Now that we know that certain API calls need to be forwarded to the broker, we will now talk about the mechanism that is used for forwarding these API calls to the broker. And that is the job of the IPC mechanism. IPC is done using a chunk of shared memory between the sandbox process and the broker process. And communication is synchronized via use of events. The IPC client is hosted on the sandbox process, while the IPC server is hosted on the broker process. And IPC calls are performed by the sandbox process to the broker process. Think of them as service requests. IPC calls can be a forwarded API call as previously discussed, or it can be a request to the broker to perform a specific action, such as launching a PDF attachment, or initializing a reader update or installation repair. To allow multiple IPC connections, the IPC shared memory is divided into 15 IPC channels. Each IPC channel has a control structure and a channel buffer. The slide shows an overview of how the IPC shared memory is laid out. By the way, since the IPC infrastructure used in ReaderX is based on Chrome Sandbox IPC infrastructure, the structure and field names used in the slides are from Chrome's source code. The IPC channel control structure has a channel-based field, which points to the channel's IPC buffer. We will discuss it in the next slide. Ping event is used by the IPC client to notify the IPC server that the message is available in the IPC channel, while Pong event is used by the IPC client to receive notifications from the IPC server that a response is available in the IPC channel. If we zoom into the IPC channel buffer, you can see that it contains the tag field and the IPC call parameters. IPC tag is a number which identifies a service in the broker. You can think of them as service IDs. An example IPC tag will be the value tree, which pertains to a service in the broker which handles anti-create file API calls. While IPC call parameters are parameters passed to the broker service. Example parameters are object names or access mask for the forward anti-create file API call. Finally, the call return field is where the return values of the IPC call is stored by the IPC server. To summarize, shown in the slides is the complete structure diagram of the IPC shared memory used by ReaderX. It is basically identical to the IPC shared memory structure used by the Chrome Sandbox IPC. The only notable difference we found is that ReaderX uses additional IPC call parameter types which we discussed in our white paper. And please refer to our white paper for a complete explanation of the fields. Now we will discuss dispatchers. This is our favorite. So why? Because they are entry points to the broker process. They are entities in the broker that handle service requests from the sandbox process. Dispatchers are grouped into functional groups or dispatcher classes. We found 19 dispatcher classes in ReaderX, and we were able to recover the names of these dispatcher classes using C++ RTTI information stored in the reader binary, and using Chrome source as a reference. Here are some example dispatcher classes. There are dispatcher classes that handles file system and registry services. Specific to ReaderX is the exec process dispatcher class, which handles services for checking updates. Also specific to ReaderX and an interesting dispatcher class is the Sandbox broker server dispatcher class. It handles services not handled by the other dispatcher classes. Example services that it provides, that it exposes are launching PDF attachment, enabling or disabling protected mode, with confirmation dialog, of course, otherwise it would be game over. Dispatcher callbacks are the actual routines that service the request. A dispatcher class can have multiple dispatcher callbacks. During an IPC call, the IPC server resolves which dispatcher callback to service a request using an IPC signature. An IPC signature is a combination of the IPC tag plus the IPC call parameter types. If you are a reverse engineer and are interested in enumerating the dispatcher class and the dispatcher callbacks in Reader X, we had provided information in the white paper for that purpose. It involves finding the IPC call structures referenced in the dispatcher class constructors. IPC call structures on the other hand contains the IPC tag, the parameter information, and the callback routine address of each dispatcher callback.
Okay, so now let's talk about the policy engine of Reader X. Policies allows the broker to specify exceptions to the restrictions imposed by the sandbox. They grant the sandbox access to certain named objects, overriding the sandbox restrictions. There are three types of policies used in Reader X. One is the hard-coded policies, the dynamic policies, and admin configurable policies. Hard-coded policies are applied by default to the sandbox, and they are added using the add rule function, which takes the following parameters: subsystem, semantics, and pattern. Subsystems indicate the Windows subsystem that the rules will apply to. For example, for file operations, the subsys files will be used, and for registry operations, subsys registry will be used. And here we can also see the difference between the Chrome sandbox and the Reader X sandbox, in that in Chrome, the subsys mutant and subsys section are non-existent, and they are unique to the Reader X. The semantics parameter indicates the permissions allowed, permissions applied to the file names or object names that match the pattern expression in the pattern parameter. So here's a list of the semantics used. And here we can also see the difference between Chrome and Reader X, in that reg deny, mutant allow any, and section allow any are unique to Reader X and can't be found in Chrome. I forgot to mention. Here are some examples of the hard-coded policies. The first line shows the rule that is responsible for Reader X being able to read any file in the system. The subsystem is subsys files, and the semantics is files allow read only, and the pattern is an asterisk. So that means the sandbox process can read any file in the system. And the next line overrides the previous line, in that it has a subsystem sys files and semantics files allow any, and it gives the sandbox process full access to the folder user app data local temp low. This is a small sampling of the hard-coded policies in Reader X. There's around 177 of them, and if you want to enumerate them all, you can use your favorite debugger to put a hook in the add rule function. But all you have to do is just find the add rule function first, which isn't that hard to figure out. Next are the other type of policies, is the dynamic policies. These are policies that has to be added dynamically due to some user interaction. For example, when a user wants to save a PDF file using the File Save As menu, the add rule function will be invoked with the following parameters. And the subsystem is subsys files, and the semantics is files allow any. And the pattern expression is the file name of the PDF file the user wants to save. Another policy type is the admin configurable policies. These are custom policies that can be added by a user or an administrator through a configuration file. The policy file is named protected mode whitelist config.txt and should be placed in the folder where reader is installed, or the folder where acrord32.exe can be found. Here's an example of a policy. The policy rule takes the following format: policy rule type and the equal sign and the parent string. Policy rule type is just a subset of semantics, and parent string is the same as the pattern parameter in the add rule function. The subsystem is implied in the policy rule type, so there's no need to specify them. And here's the policy rules. And so far we have discussed sandbox restrictions, the sandbox startup sequence, interceptions, the IPC mechanism, and policies. We will now talk about the security aspects of the sandbox.
Now we are in the second part of our talk. This is the part where we discuss the security aspect of the redirect sandbox. First, we will talk about the limitations and weaknesses of the redirect sandbox. We will assume that the sandbox process is already compromised in one way or another. And the question now is, what can a malicious code do once it is running in the redirect sandbox? A sandbox code can steal sensitive files such as documents and source codes, since there's a hard-coded policy rule which grants read access to all files accessible to the user's account. A sandbox code can also steal the contents of the registry, which may also contain sensitive information. There are hard-coded policy rules which grant read access to major registry hives, such as the one shown in the slide. Clipboard read and write access is also possible because clipboard restrictions are not set on the job object. And there's also the Sandbox Clipboard Dispatcher in the broker, which provides clipboard-related services. And most importantly, a sandbox code can still obtain a socket descriptor and use it for any purpose. Combine this limitation with read access to the file system and the registry and a clipboard, it is indeed possible to conduct an information theft attack without escaping the redirect sandbox. Also, we found some permissive write-aloud policy rules to certain files and folders, some of which are used for third-party applications. An example of which is the one shown on the slide. A sandbox code can leverage it so that an attacker-controlled JavaScript code is executed every time a new instance of reader access is spawned. In our demo, we will show you how a sandbox code can leverage this particular weakness to achieve a limited form of persistence. And finally, since FAT partitions, which are still used in USB flash drives, have no security descriptors, a sandbox code can modify or create files in these partitions. A sandbox malicious code can leverage this for propagation purposes. To summarize, it is possible to carry out information theft attacks without escaping the redirect sandbox. Adobe is aware of that, and they plan to extend the sandbox to restrict read activities and are investigating ways to restrict network access in the future. And as promised, we will demonstrate a proof of concept information stealing exploit payload at the end of our talk to prove that we are not making this all up. Our next focus is sandbox escape. We will enumerate ways for a sandbox code to escape the reader X sandbox. The first option for a sandbox escape is exploiting local privilege escalation bugs. This is a generic technique and applies to other sandboxes as well. The ones that are interesting are those that result in kernel mode code execution. Because, for example, you can have a generic kernel mode payload which changes the token of the sandbox process to the one used by the system process. So suddenly, you will have a sandbox process that has more privilege than the broker process. A sandbox escape method described by Tomkich in his papers is named object squatting. Since the sandbox process can still create name objects in the local namespace, it is possible to craft malicious name objects that are trusted by higher privilege process. An example attack involves exploiting parsing bugs in higher privilege process, such as the one demonstrated by Tomkich against protected mode, IE. A sandbox code can also leverage the write aloud policy rules to escape the redirect sandbox. Some of these write aloud policy rules are used by the broker and other third-party applications, which generally runs in a higher privilege level than the sandbox process. As long as you can control the behavior of higher privilege applications, there's always a risk and / opportunity for a sandbox escape. An example scenario is when a higher privilege application fully trusts a configuration data that is writable to the sandbox process. If, for example, the configuration data contains executable file paths or library file paths, a sandbox code can modify these file paths as an attempt to execute code at a higher privilege level. If you are a reverse engineer, you can use the example policies we had shown in our previous slides to find the rest of the reader X hard-coded policies. The last 3 slides pertain to the attack surface in the broker. The IPC server is the first code that touches potentially untrusted data from the IPC shared memory. It is the one responsible for verifying the contents of the IPC channel buffer and serializing IPC call parameters from the IPC channel buffer. If you are a reverse engineer, we had provided address of the functions shown in the slide, so you have a starting point in your trace. And of course, there are dispatcher callbacks. The large attack surface in the broker is due to the number of dispatcher callbacks that are callable from the sandbox process. These dispatcher callbacks runs in the context of the broker process and uses untrusted input from the sandbox process. So a weakness in any of these dispatcher callbacks can lead to a sandbox escape. Again, if you are a reverse engineer and are interested in enumerating the dispatcher callbacks in redirects, we had provided information in the white paper for that purpose. And finally, a weakness in the policy engine could allow a sandbox process to write to the sensitive parts of the file system or registry, which in turn could lead to a sandbox escape. If the file or register entry is used by the operating system, the broker, or third-party applications, which runs on a higher privilege. The first step to find a weakness in the policy engine would be to understand how the policy engine performs policy evaluation using the policy rules. You can start by studying the policy engine source in Chrome and then proceed in tracing the policy engine calls in the reader X dispatcher callbacks. And once the operation of the policy engine is understood, one will then need to find a way to influence the result of the policy evaluation. To summarize, a sandbox escape involves attacking the broker process or other higher privilege applications. And as a rule of thumb, if a sandbox code can control the behavior of higher privilege applications, there's a risk or opportunity for a sandbox escape. Now we will be going to our demonstration. The demo involves conducting an information theft attack without escaping the reader X sandbox. In the demo, we will be using reader X 10.0.1, not the latest version, because the demo involves exploiting a known bug, CVE 2011-0609, to gain reliable code execution in the sandbox process. Nonetheless, we verified that this demo works on the latest version of reader X using manual injection of the payload in the sandbox process. The Windows XP machine is the attacker's machine, which serves the exploit PDF file. The Windows 7 machine is the victim machine, which have reader X installed. In this scenario, the attacker wants to steal the documents of the victim. To prove that this is not a fake demo, we may ask someone in the audience to give us 3 random numbers.
One.
All right. All right, 1 and 7.
5.
All right, 1 and 7, 1, 7 and 5. All right, thank you. Okay, the attacker will now entice the user to click the malicious, a malicious link to the PDF file. So this is the link, and then the user will click it. So it says the POC PDF file is sent.
Wait. What's that?
All right, so as you can see that there's some you can see that there are some registry keys are now stolen. And there's a list of the user's files. And the content of which is the randomly chosen number. But the demo doesn't end there. Notice that the sandbox payload modified the config.js file. What this allowed the attacker to do is to re-exploit the victim's machine every time a new instance of reader X is spawned. Here's the contents of the config.js file. So what it basically does is to load this particular URL using the default browser. Now let's assume let's close this. Now, let's assume that the user created another document, and let's call it corp secret v2.doc. Okay, so in this one, we will just increment the randomly chosen numbers. Okay, so you will see that we will not be visiting the malicious link now. What we will be doing now is to create an instance of reader X. So you will see that in a few moments, you will see that the link is automatically visited using the default browser, which then causes reader X to be exploited. So you will see this, you can see that this is the new file that we had just created and the contents of the file. And remember that all that happened without escaping the reader X sandbox.
Okay, so now we're going to our next demo, which basically uses the same exploit for the same reasons mentioned by Mark. And we'll just wait for the snapshot to restore. Okay. You can see. Okay, so here we have an innocent looking PDF file. And then we will open Reader to show you that the sandbox is currently active or on. Okay. Now, the user, here's a scenario where the user wants to open the PDF file. So, open it. Then the user sees the following message box, which tells him to reopen the PDF file. But what the user doesn't know, and what you, the audience, don't know, is that at this point, the sandbox has just been disabled. So yes, we achieved one of our goals in starting this research, and we have found a sandbox bypass vulnerability in ReaderX. And to prove that, not yet. And to prove that, and here's our favorite payload. And if you look at Process Explorer, you'll see that it's not running under the sandbox. Okay? So that's it. So that concludes our presentation, and if you have any questions. Oh, we can't talk about the vulnerability yet in detail, since it's still under disclosure with Adobe. So no questions about that. Any questions?
Any questions? Yes, sir? Can you repeat that, sir? I haven't tried it, but you could probably try it.
Any question?
No? Any question? Capture it. Anybody have a question? All right. Thanks for coming on.
Thanks for listening. Have a good night.